This video will cover a solution guide to problem 76 from chapter 9. The pulley in the picture has a radius of 0.16 meters and moment of inertia of 0.38 kilogram meters squared. The rope does not slip on the pulley rim. Use energy methods to calculate the speed of the 4 kilogram block just before it strikes the floor. This problem can be solved with conservation of energy. We have solved this type of problem before. The only difference is that now we are concerned with the effect of the pulley on the system. So, we need to consider the kinetic energy from the two masses and the pulley, and the gravitational potential of the two masses and the final and initial conditions. We know that the kinetic energy is defined as 1/2 mv squared. However, we were not given the mass of the pulley. Instead, we were given its moment of inertia and the radius. So we need to put the mass in terms of I and r. The moment of inertia is defined as the mass of an object multiplied by the square of its radius. Rearranging that to solve for the mass, we find that the mass is equal to the moment of inertia divided by the square of the radius. So the kinetic energy of the pulley can be expressed as 1/2 multiplied by the moment of inertia over the radius squared, multiplied by the square of the linear velocity. Let's start by figuring out which terms in this equation are non-zero. If we assume that the system is initially at rest, the kinetic energy of each object is 0. The only object with gravitational potential energy at this point is block 1. It is a height h above the floor, so it will have a potential energy of m1gh, while the other objects will have potential energy of 0. Just before block 1 strikes the floor, every object will contribute to the kinetic energy. The kinetic energy for block 1 will be 1/2 m1v squared. Block 2 will have a kinetic energy of 1/2 m2v squared, and the pulley will contribute 1/2 I over r squared all multiplied by v squared. Block 2 will now be a height h above the floor and will therefore have a gravitational potential energy of m2gh, while the other two objects will have the potential energy of 0. Now, using our table, we can rewrite our conservation of energy equations in terms of non-zero values. So initially, the system just has the gravitational potential energy from block 1. In the final situation, we have the sum of the kinetic energies from all three objects and the potential energy from block 2. Plugging in the expressions from the table, we can see that we have three terms that involve the linear velocity. Our goal is to isolate and solve for the linear velocity, so we will subtract the potential energy from block 2 from each side, and then factor out the v squared term from the right side. Isolating the v squared term, we find an expression involving all known variables. Taking the square root of this expression and substituting in the values given to us in the problem statement, we find that just before block 1 hits the ground, the system was moving at a speed of 3.07 meters per second.